Okay, so in this video, we're going to talk first about a really important theorem because you might have noticed that up to this point, we've been dealing with series that have non-negative terms. So we have to figure out, well, what happens with those series that have some terms that are negative. So we'll start to think about this, and we'll continue with alternating series in the next, probably that will happen in class next week. But absolute convergence is very strong convergence. It says that if the series in absolute value, when the terms are in absolute value, converges, then when the terms are not in absolute value, that series will also converge. So basically, taking a series in absolute value and showing that that converges is a stronger convergence than anything else. So when you add some negative terms, the series will still converge. I'm going to do a very quick proof of that, and then we'll do some examples to better understand it. So when we take any term a sub n, it's always less than or equal to itself in absolute value and greater than or equal to the negative of itself in absolute value. That's always the case. You can try it out with some numbers if you'd like, right? Like if you think about 3 or negative 3, let's say, is always less than or equal to 3 and greater than or equal to negative absolute value of negative 3, which is 3. And that's a true statement. So this is always a true statement. And I'm going to work with this true statement to get to our theorem, the statement of the theorem. Which is that we'll assume that the series in absolute value converges when the terms are in absolute value. So the first thing I'm going to do is I'm going to add absolute value of a sub n to every part of this inequality. And so we'll have 0 is less than or equal to a sub n plus absolute value of the nth term, which is less than or equal to 2 absolute value a sub n. Okay, so our assumption is that the series when a sub n is in absolute value converges. Because this is true, we can also say that 2 times the series of absolute value a sub n converges because we just take out a 2. It's still going to be convergent, right? So we know that the series whose nth term is 2 absolute value a sub n will converge. And so by comparison, since this is smaller than 2 times a sub n, right? If we do a direct comparison here, then we know that the series whose terms are a sub n plus absolute value of a sub n must also converge, since all of its terms are smaller than the terms of a series that converges. And so if this converges, we can split this up, right? This is equal to the sum of a sub n plus the sum of absolute value of a sub n. And we know that this series converges by given, that's what was given. And since we know that, since all of this must converge, then this series must also converge since the sum converges. So this must also converge. And we're done, right? That's just a short proof that shows that if a series, when you take the terms in absolute value, converges, then the series without absolute value will also converge. Let me just show you some examples. Let's suppose that now we're dealing with an alternating series that looks like this. Negative 1 to the n plus 1 times 1 over n squared. So here the terms alternate, positive and negative. You can list out some terms if it's easier for you to see. But the key piece here is that we know, right? We know that the series in absolute value, so just 1 over n squared from n equals 1 to infinity, this series converges because this is a p series with p equal to 2, and whenever p is greater than 1, the series converges. So since this converges, which means that our series in absolute value converges, right? What we've just seen is that our series, when you take the absolute value of negative 1 to the n plus 1 times 1 over n squared in absolute value, that's the same as the series 1 over n squared, which we know converges. And so since the series in absolute value converges, then our given alternating series also converges. So therefore, given alt series also converges. Alternating means terms go positive and negative. So all I tried to show here is that if we have a series, I don't know its convergence, but the terms alternate from positive to negative, I can look at the absolute value of that series. If in absolute value that series converges, then our original series also converges. So one more example, then I will post this video and do a separate one for the ratio test. So let's suppose now we've got a series that looks like this, n equals 1 to infinity of sine of n over n squared. Now, sine n takes on values from -1 to 1. So there are times when this is going to be a positive term, times when it's going to be a negative term. Now, if I take the whole thing in absolute value, right? If I want to show that this in absolute value, so to show that this series in absolute value converges, because if I can show that, then my original one also converges. So I'm going to take the nth term of this series, sine n over n, and show that in absolute value that will always be less than or equal to 1 over n squared. This is always the case because sine n in absolute value is always less than or equal to 1. And so because this is true, again, 1 over n squared is a p series. That's Lucy. Okay? P series, p equal to 2, which is greater than 1, so this converges. So by direct comparison, we have that this series also converges. So this converges by direct comparison. I'll just write by comparison. And so since the series converges in absolute value, then we can say that our original series, which did not have absolute value, will also converge, because in absolute value it converges. So basically, convergence with absolute value is the strongest kind of convergence. That is what this short video has been about, right? So just an important theorem that if a series, when we take all its terms in absolute value, converges, then when you take the absolute value out, it will also converge.